Welcome everyone. This is Khalil. Today I will give a presentation on realistic transport simulation for studying the impacts of shared micromobility services. Shared micromobility services see increasing deployment in urban areas, and new services have emerged in the last years. The question that we are trying to answer in this work is, how much car traffic can be reduced during peak hours if this e-scooter service is deployed? To do that, we need first to prepare synthetic agent plans and then run the simulation. After that, we can analyze the results and understand the effect of e-scooters. We choose the campus of UAB as the target area to study, since UAB is functional zone for education, research, and healthcare. We use a survey that contains approximate home and work location for students and employees. And we need to sample the following locations in order to create realistic plans for the simulation: home locations for students and employees, work locations, parking locations, classrooms, and e-scooter stations. We face some challenges with the data sources. The first challenge is that student locations are not exact to protect participants' privacy. So we used an address geocoding API to get approximate locations. Then we separate the locations into two sets, on campus and off campus. The second challenge is that we need more data than what we have in the survey to generate a realistic simulation. So we use the kernel density estimation to fit the 2D location distribution. Because some students and employees need to find a parking location, we proposed a scoring function to give a score for each parking location. We also use Poisson distribution to decide if a parking location has the capacity for more cars. For the traffic simulation, we use an agent-based transportation simulation software called MatSim. MatSim takes the travel day plans of a population and executes them on the underlying road network to generate simulated traffic. We consider three types of traffic that constitute the majority of UAB traffic: background traffic, where travelers are just passing through UAB; traffic generated by students attending classes; and traffic generated by employees going to work. For student plans, we adopted the three types of plans: students who are walking to the classroom, students who live off campus and drive to a parking location, then walk to the classroom, and the students who live off campus and drive to the classroom. Employee plans are similar with some minor changes. We also need to sample the time for each activity. In the case of students, and since we already know the class start and end time, we calculate the time to leave home, the time to arrive at the parking location, and the time to arrive at the classroom. We also add T1 to impose diversity, which sampled from a normal distribution. We use the same techniques to sample the leaving class time, adding T2, which is sampled from exponential distribution. We conducted our simulation using 500 e-scooters, 22,000 students, and a total of 20,000 employees. We measured the hourly volume and the average speed on two major road segments at the center of UAB. They are the 14th Street South and the University Boulevard. Our results shows that using e-scooters clearly reduces the car traffic volume in almost all hours. Also, the results proved that allowing e-scooters generally increases the speed, especially during peak hours, indicating that traffic flow is improved when using e-scooter mode, which reduces congestion. We can visualize the traffic simulation result around UAB at different hours. Triangle icons represent cars, where the colors mean different speeds. We also can see the bicycle icons that are used to represent e-scooters. Thank you so much for your interest and attention.